Thank you very much, Bob. Bob has done a number of sessions for us in the past, and lots of interesting things that are applicable in the classroom. I got a lot of use out of the small scale reduction of copper oxide that you showed us a number of years ago. The best way of doing the copper to oxide to copper on the small scale was brilliant. So I always think that if you can come away from one of these sessions with one or two things you can apply in the classroom, then it's a very good course. So thank you very much, Bob. I will pass over to you. Thank you.
Well, thank you very much. The title of this is Sir, Madam, Your Experiment is Served. And this arises because in February 2019, I delivered my last workshop to over 20 people at the University College London in the Education Centre. And it was, I must admit, one of the best I've ever done. And it was helped by my colleague, David Patterson. More of that at the end. But we produced lots of experiments, and there were wonderful moments when old traditional teachers suddenly realized that they were seeing some things that they'd never seen before. Anyway, all of a sudden, the whole system closed down. What was to happen to practical work in the United Kingdom? CLEAPS is the organization which handles all the safety. And we had to be in direct contact with the Department for Education, and we had to take down many, all their kind of instructions on how to proceed in a lockdown situation. Some students were working in bubbles, some were not allowed to come to school at all. It was a little bit of a mess. The idea of doing experiments on a tray appealed to me, because what happened was that in my workshop that I'd done in February, and I'd done a few before then, I do several demonstrations and practicals where everybody takes part. And then all of a sudden I said, right, here's a box of chemicals and equipment. Here are some instructions, and you can therefore try it out yourselves. And this is how we went on. So I thought, well, all we need to do is to take the box, convert it to a tray, and we've got a tray of a practical. So we had to produce a guide for the country, and of course it came into quite a bit of criticism, but it wasn't really our fault. We had to try and interpret what the Department for Education said and then apply it to practical chemistry. And what I'm going to do is I'm going to stop and in a little while, you can ask some questions at certain times, and we'll deal with them as we go through. So luckily, when we produced the guidance of practicals that you could do, Matt Endine, our assistant director, and Steve Jones, our director, I said to them, look, what about some microscale chemistry? We can do that on a tray in a room. It's what happens around the world. And so we came up with this proviso that you can do some any sort of practical in an ordinary classroom as long as no heating is required. I must admit, I didn't fully agree with that. I think you can use some heating, but I was just happy to have this going on. So these were certain experiments which you could do. And here's an example of a one tray chemical, and it's the one I always introduce many people into the practical work, and you make put buffers onto plastic. If I just stop there, this is a plastic sheet, and I put the instructions on a piece of paper and I insert that into the folder. And then all we do is to do the drops of each buffer onto the columns, and into the rows we do the and you get a wonderful picture here of the different colors of the indicators, and they're in front of you. If you think about this from a technician's point of view, I would have used 25 test tubes to do this experiment. They would all need to be cleaned afterwards. All I do is take a paper towel and wipe it off. And what we've shown here is that if we make a mixture of bromothymol blue, methyl orange, and phenolphthalein in that sort of order, we can get quite a nice universal indicator. And we can compare that with what we make up in the lab or what you can buy. And actually, I think ours is slightly better with the methyl orange. The trouble is that this is made with methyl red, and methyl red's a much cheaper chemical than methyl orange, so that's why the suppliers use it. It's called the Yamada recipe, which they usually supply. So, we'll just play this again, and you'll see how it's done. So I hope you see there's the sheet, and you can see the plastic folder. You put it in through the right there. And you can laminate these if you want, but I never do because I always make spelling mistakes and I always get annoyed about that. And my great friend in America, Bruce Matson, who in fact developed that experiment about copper oxide and hydrogen, Jill, he called these puddles. I've rather taken to the idea now, so we call it puddle chemistry. So that was an example of the puddle chemistry. And you see, this is why I don't laminate anything, because I should have written out there a Dropbox resource, and I can't spell. Anyway, so what we have here is what I did was move from the chemistry out of a box to the chemistry in a tray. And there you see a reference to the to the Dropbox, and you can see there all the items I've got. They're all in PowerPoint. I make these instructions in PowerPoint so they can be inserted into the plastic container. We'll look through one in a minute, and but you can go to it and find it out. And if you want to contact me later on, some details will come up. So there they are. So if you have any questions at the moment, have anything come up in the chat, Mark, that you?
There's nothing.
No, nothing yet.
Nothing there. Okay, that's good. That must be boring everybody. I mean, you should be asking about why it was such a. It was a really difficult time sorting out how to do practical work in schools. The Department for Education put in a word, meticulous, and the Department for Education serves England, but the Scottish and the Welsh and the Irish did not put that word in. So their jobs were easier for cleaning than in England. And that's the sort of thing we had to struggle with all the time with the Department of Education. Anyway, there we are. There are some links. The first one's my Cleeps link. I do an awful lot on Twitter, as you see there. I only use Twitter for chemistry. I don't do it for anything else. There is a YouTube channel. If that's too complicated, you can. I'll put these into the chat box later on. You can actually just put in Bob Worley YouTube. I just realised that I'm a chemist and not a banjo player, and you will realise, and you'll get to the video to the YouTube channel. And we've just started some articles in science in schools with Adrian Allen, a friend in Scotland, and that's taken off quite nicely as well. Okay, so let's go to the actual one of those PowerPoint displays that we get. So I start with a kind of summary of what you can do, and this is just a simple one with just different acids and alkalis and the different universal indicators. You'll see I'll take this much further later on. Here we have the one that we've just shown you, so you can try this yourselves. You've got to realize that you've got a reversible reaction here, so you can go from acid to alkali, the color, and you can go to and fro all the time. So it's the indicator is a good example of a reversible reaction. It is as good, if not better, than the traditional one they put into textbooks, which is the dichromate to dichromate 6 to chromium to chromate 6, orange to yellow. It's actually safer and better. You can use these ideas as starters for 10. You don't have to spend half an hour on a practical. You can just take 10 minutes to do the practical and then talk about it. Many of the experiments are done much quicker by this method, and you've got them there and talking about the practical and all the ramifications of it in the time that you would normally be messing about, running around the lab and doing all sorts of things. Everything is on the tray. I got this idea from the education research Royal Society of Chemistry Resources. They do lots of questions and that sort of thing, but they don't do any practicals. And I thought an introduction like that would be good. And here's a typical one. Now, this is from David Patterson, and he has produced, well, goodness me, the copyright is in the future. Anyway, he has produced a whole series of what we call interactive worksheets. So what you do is you focus the student on the experiment there in front of them. They are not walking around the lab having to pick up things or collect things. The 2 dropper bottles, the water, and the small amounts of crystals of sodium carbonate and citric acid you need are already there. So that's all you need. Drops of water, universal indicator. And what he does is he does something I don't do, but he puts those little squares in so a student can actually mark on the plastic that they have done, number 1, added 20 drops of water to the central circle, add 2 drops of universal indicator, and deal with that like that. So you then add the crystals to it. I thought you might like to see this because it is rather remarkable. Now, these are rapid. These take 6 minutes to do. And when I first did this one, I was actually amazed when I saw the bubbles of carbon dioxide forming in the puddle. So that's citric acid at the bottom and sodium carbonate from the top. This is the bromothymol blue one. You don't have to use a mixture, and again you get the formation of the bubbles of carbon dioxide at the where the 2 solutions are meeting. Well, I must admit that was a bit of a wow moment for me. And I know that one of the issues, objections to Microscale is that it isn't really wow. It's not explosions or fire. No, it's something different, and it's appealed to me in my old age. It's something rather beautiful about seeing bubbles appear like that. You'd know they ought to, but just seeing them was rather remarkable. So there we have. Of course, you might say that going from red to blue like that is the colours of the inclusivity flag as well. So anyway, so I'm politically correct as well. So I hope I'll show that one again because I think it's rather beautiful. This takes 6 minutes to do, so I've speeded it up, and there's the formation of the alkali side, the acid side, and at the interface you start to get the bubbles. I've actually wondered if there's a real meaning in the bubbles appearing just inside the alkaline position, but I've never really satisfactorily explained it myself. Well, perhaps it's moving towards this acid now as it settles down. There it is. Okay. No, you can make them. Now we can go into the sixth form, and we can. Nasco, if you write the question down, I'll answer it in a few minutes. Okay. So if you see the pH, you can actually understand a bit more about buffers. Now, I had a bit of a problem here. Should we actually have 14 different buffers in front of me? But I found that if you buy buffer tablets or buffer powders, you can make here the standard buffers at 4, 7, and 9. But I found that if you added buffer 7 to buffer 4, you can actually make buffer 5. So what I was doing was to measure the pH of my buffers with a small portable pH meter, the Hanna Checker, which I find very useful because it's got a very narrow glass bulb there. So you can make all these buffers quite easily, and then you can produce profiles and things like that. And during the summer, a group of us got together and started to go into our gardens and find the plants. And you take the flower or a leaf or a skin of a fruit, you put it into water, you can just boil it up and the dye comes out, and you can check the color at the various pHs. It was actually fantastic. We were found one of the best. These are the best flowers I found. The first one is the butterfly pea. Now you probably don't know what that is, but it's rather an exotic tea that comes from Thailand, and you can buy it online. It's an extremely deep color, and a little goes an awful long way. And the thing is, it doesn't smell like red cabbage. In fact, if you want, you can make yourself tea with butterfly pea, and if you put the tea into lemon, then you get the red color appear. So you get an exotic drink which is half red and half blue. But these colors here in the alkalinity range were amazing as well. And these were the pH profiles of the Tradescantia plant. That's a plant I've had for nearly 50 years. It keeps coming. I brought it. It's been from Uppingham, where I started, to Norwich, where I did some more teaching, and now back to London. It's the same plant, and it just keeps flowering every year. That's my Tradescantia plant, and the lobelia as well. Both beautiful colors you get. This is the anthocyanins from the oxalic on the oxalis leaf, which I drove a garden. I was so, and this is beautiful. The yellow here is just simply amazing, and the colours change as you go from alkali to acid. By the way, these anthocyanins also form colours with metals, and I've been able to tell the difference between zinc and aluminium ions by the use of these anthocyanins. So don't just try them with pHs. If you do get them, make them into, have a look at the reactions with metal ions as well. It's quite interesting. Ian Smelly of St Andrews University has written an awful lot about it online as well. And you can understand how buffers work. So, Dasco, any questions?
There have been a couple in the chat, actually, Bob. So,
Yeah.
First of all, one was when you recommend your puddle chemistry there, which, as you say, saves washing up a lot of test tubes. Are there any particular type of dropping bottles that you would recommend to teachers to use?
I'm going to show you some equipment later on, so I can answer that. But basically, no, they're just plastic, like what you get sometimes to eye drops and things like this. But you can buy them online. They're quite cheap. They're quite inexpensive. I don't like the word cheap. The word is inexpensive. I was so pleased that the Royal Society of Chemistry's Secondary and Further Education Group, we put on a presentation this summer, and we got a lot of interest from all around the world. And I thought I'd just show you how other countries have to cope with some of their conditions. In China, they have wonderful glass workers. I was absolutely knocked out by the glass equipment that they were using. It was beautifully made. It's an art that our scientific glass blowers, we don't have enough of them in this country now, but that was really wonderful to see. But they're working at the school desk. This is from a colleague in Vietnam, where they're all working in a classroom. Notice how they're all sitting down, and that is something that is strange to us in the UK. I mean, we have it in our lab rules, don't we, that you mustn't sit down in case you get spills on your lap. But of course, if you're working with these sorts of volumes, the spills just don't exist. Huh? Then my colleagues in Thailand, they're doing a wonderful job in promoting Microscale. Fortunately for them, the company Dow Chemicals has decided to finance the whole chemical education in Microscale, and that's how important they want people to take on to become chemists, and they think that this is one way of doing it. And then in South Africa, John Bradley produced the Radmas kit 30 years ago, and that was to bring chemistry to students in the Veld in South Africa, where they had no laboratories at all, just benches. And that project was taken on by UNESCO and sent to all over the world, and to East Europe and to Malaysia and Mexico. It went all around. There were some barriers, and I shall talk about those in a little while. So I have laboratories and all the right chemical equipment at school. Why should I change? That is a very common comment I get in the UK. sorry. I've already found that this sort of chemistry improves safety. Obviously, there's going to be lots of green issues solved by this process. It's going to it reduces the cost. That is a problem because it means that the suppliers are not going to make big profits out of it. And so they would like to produce kits. And I don't like kits, but we've seen that it promotes practical science in developing countries. And to us, it has produced some practical science during the pandemic. Now, these countries use kits, but I find if you have a kit and you do one experiment more than the others, you use up that piece of kit quickly. So you've got to buy more of it. And so you really need to keep your fingers on how much you've got, and that's a big job with kits. So I don't use a kit. I use equipment that you find in our school labs, but not always. I feel like Eric Morecambe here, but not in the context that we usually have them use them. For instance, in chemistry, I use Petri dishes a lot, and Petri dishes are found in the biology department. But we're fortunate in the UK, we have some fantastic technicians, and they have contributed an awful lot to the process. So yes, these are the negative the negative comments that I have received. Microscale techniques are not mentioned in the examination specifications. Well, they are, but it's hard to find. Now, this one came up on the school technicians' Facebook page only yesterday. Students are at a disadvantage in exams if they carry out these new procedures, even though they provide better information and evidence. And that one really does annoy me, because I'm trying to teach these students chemistry. Here's a good method, yet I can't use it because it's not the version the exam board wants. But you can do both at the same time. You can film one or get the students to do one. You can compare methods. It does need a little bit of thinking. This one came up in the discussion yesterday as well. They don't do this sort of thing in universities or in industry. Well, what is an LTF test if it isn't microchemistry? If I'm going to put a little swab up my nose and in my throat, put a little drop onto the filter paper and look at that solution move along, and then show that I have not got COVID, thank goodness, then I am doing microchemistry. In fact, it's more than it's nanochemistry. They are not mentioned in textbooks and revision manuals. Well, the problem is that authors never come to the workshops, and so it is difficult to overcome that. But more of that at the end. The others, yes, it's not I was taught. Yeah, well, sort of. But teachers don't have time to go to workshops and to go to ASE conferences and to see these things done. This lack of CPD. Now, 12 years ago, we had science learning centres, we had teachers' TV, and it's all been thrown away. All that marvellous initiative that we had. The quantitative work will not be accurate. Evidence? Well, you'd be surprised. Anyway, at that point, any more questions, Mark?
No further questions.
I'll carry on. I will carry on. Okay, so equipment that might be new to you. Now, they're the dropping bottles you can buy, and all the suppliers sell them, or you can buy them online from online sources like Amazon and people like that. A game changer has been this balance. These balancers cost less than £10, yet they weigh to 2 decimal places. Are they accurate? Well, try and put a mass on, and you'll find that They are fantastically accurate. You can get them to 100 grams, and they will tear to 100 grams as well. You'll see one in use in a minute. And there's the plastic sheet which we use, the plastic folders, to do some precipitations on. Now some equipment needs to be made. So just let me go through this. This is the microelectrolysis cell. The details are on the CLEEP's website, and people can always ask me, and I always pinch it and give it to people if they're interested. But that's on the CLEEP's website. That is the microelectrolysis of copper chloride. This is a conductivity indicator, and you'll see that in use after the break. This is the a spirit burner. I never used to like spirit burners until I started to do this, and I found that the spirit burner works fantastically well, as you'll see later on. And I get these little jam jars from the local hardware shop, and it doesn't take long to make a spirit burner. More sophisticated is this colorimeter. This colorimeter is based upon Lego. I hope you see that. And it works with an LED. So you have an LED with a certain color, that's your filter, and you have a near infrared LED to collect the light that comes through the cuvette, and that will then produce a voltage in your voltmeter. That is so cheap. We developed that for the biologists at CLEEP's. They wanted an inexpensive colorimeter. We found this in Journal of Chemical Education. We've made our own version. Actually, during the lockdown, I actually used a large Tic Tac box. Tic Tac sweets came, and they take the place of the cuvette just as well. And the results are very encouraging. I can tell the difference between Diet Coke and real Coke by just comparing the colors of the solutions. On the right here is my little Hoffman, as I call it, and this is the most expensive piece because it has two small little pieces of platinum wire in there. But I use sodium sulfate as the electrolyte, which means that when you put the current through from the battery or from a low voltage supply, you get an alkaline region around the negative electrode and an acid around the positive electrode. And if you look at my last tweet, I just put it online today. I actually put pH probes in there, and I got a reading between a pH of 0 up to 15. I think I broke a record there. So that's the equipment that needs to be made. Other sources, well, this is from medicine, and using these syringes. These blunt needles are really, really good, and that they're getting their use. I'm getting used to using them. If you want a well plate, then a blister pack works nicely. Just peel away the aluminium. Have a headache first, of course, then peel away the aluminium, and you've got yourselves a little well plate. This is the tray that I got from Wilco's, the hardware shop. These are really useful for keeping, for holding petri dishes and things like that. This is a microwave container that can act as a hot bath if you want. And the bottle tops, I like collecting these because they usually have had beer in before. And then I use that one. That is actually the oxidation of magnesium to magnesium oxide. You do it in the bottle tops, and every person on my workshop got an increase in mass on this experiment, and it's such a difficult one with students. Basically, you just make the sandwich, heat it up strongly, let it cool after 10 minutes, and then weigh it again, and your cost will increase. So the actual experiment really does work. So if you want to see a gravimetric titration, this is the first of my titrations where I start to use a balance. So there's a drop of phenolphthalein in the vial. I add 1 ml of diluted vinegar, and note the increase in mass. And this is the way I deliver the drops, and just by turning the screw on the, and once it goes permanently pink, you can then weigh it again. Now in America they have rubbish clamps, so I had to invent something, and I invented this. It's a bit crude, but it works. And then you do the third weighing, and work it out, and it comes to, well, I have had a comparison done with titration, and we came to the same value. And you know, it's just mind-boggling that it works. But this is an introduction into titration. I know they've got to do a proper titration with burettes when it comes to an exam. Okay, but have you ever seen the 14-year-olds using your burettes? It's frightening. There's 13 pounds going up the chute every time you get them to do it, and there's a lot to think about. It's too much for them. It's what we call overloading the workplace memory. Okay, so let me go to the. I think I've got another one. This one I think it can only be done microscale. I did this in the lockdown, and this is the milk of magnesia, because you can't really make a solution of it. It just sinks all the time. So you have to shake your milk magnesia awful lot. So you put the drop in and put it onto the balance, and then you get your milk of magnesia solution. You have to shake it again, get a 1 ml, put it in, and you get this suspension, and you weigh it. Now we shall do the titration. Now you see the technique of turning the screw on a British clamp. They're the best in the world. And you're trying to get, it's a slow reaction. So you see it goes red as the acid is added, then it goes back to yellow again. So it's a good example of reversible reactions again. This is a bit boring as I try to get there. I always think this is the last one, but it never is. And the red color lasts longer the closer you get to the end point. You'll now notice something interesting. The solution's getting more transparent. And that's because the magnesium hydroxide is in fact, oh, no, it's gone back again. So one more drop, that should do it. Okay, so there we are. And oh no, it's going back again. There, right. So there we are. And let's weigh that again. And just let me hold it there. So there's the result. That one gave a percentage of magnesium hydroxide in the milk magnesia of 7.4%. The value from the data sheet provided by the people who sell it gave me 8%. I did another run and I got 7.5%. So there you are. It is not a bad way of doing the titrations. Well, I think I've just hit the right spot for the end of the first part. Are there any more questions? I'll stop the share there, so I go out. Oh, more people.
There were a few joined as we were talking as well. There are no further comments in the chat unless anyone has one they wish to raise their hand virtually.
Have I answered the question about the dropper bottles? Who asked that question?
That was John, actually.
Yeah, Bob, that was great. Thanks for that.
Is that all right?
Yeah.
Yeah, they're quite easy to obtain. Most suppliers do sell them now, and if actually you get, 50 for £10 or something like this, they're quite reasonable, and the technicians can produce them for each. The problem is there are a couple of solutions that don't work very well. Iodine solutions discolor the plastic, right? You've got to be a bit careful with ammonia because it leaks, and also what's the other one? Ammonia leaks. Oh yes, sodium hydroxide. If it's too dilute, it goes off to sodium carbonate. You just got to keep your eye on it a little bit. And hydrogen peroxide goes off a bit as well. But on the whole, most solutions will keep for an awful long time. Interestingly, when I've made these syringes of gases, by the way, I had to do a course in Scotland, and I had to go to Scotland on a Monday, and I had to make the solution, my gases, on the Thursday. And I made gases, I kept hydrogen in those syringes from Thursday to Monday with no problem at all. I've put these contact details on the chat line for everybody, so you can have a look, and also my website, which I really must get round to sorting out soon. Anyway, so here we go with the second part of this. I'm probably going into a little bit more detail. So I started teaching a long time ago, in 1970, in fact. And I started at Uppingham School, and then I moved in 1974 to Norwich. And in Norwich, there was a fantastic group of chemists, chemistry teachers from both independent and state schools. And we used to meet at the University of East Anglia under the guidance of Professor Malcolm Fraser. And Professor Malcolm Fraser knew Alex Johnston. So Alex Johnston was a professor of chemical education at Glasgow University. And he was a teacher to begin with, and he knew there were problems in teaching chemistry. Everybody loves the macro events in chemistry. These are the wow moments. Magical, beautiful, colourful, all those, and even the weird. And everybody loves those. And if you start a lesson with the youngest students and 11-year-olds, you do your first lesson, it's mind-blowing. They all come to you and they'll say, that's fantastic. I never did a lesson on safety to begin with. It was always a presentation of what they might get. Anyway, so this is what, because I remember when I went into a laboratory in my old school in 1957, I saw copper sulfate solution and I was hooked. That was it. I knew what I wanted to do. So there it was. But there's a problem with teaching chemistry. First of all, there are some nice things like the periodic table, lovely stories, but then there's those awkward things like chemical equations, mold we never did mold calculations in the 1960s. Everything was done by proportion, so we never had these problems. But these things have kind of filtered down into the 11 to 16-year-old syllabuses, and also we find explanations of how they can. Remember that all these particles are tiny and invisible. Here's a mind-blowing fact. In 18 grams of water, we know there's the Avogadro number of molecules. That is the same number that is estimated to be the number of stars in the universe. That is something that is actually quite mind-boggling. And being able to think about these chemistry at this level is so difficult. I think it's part and parcel why people can't really get hold of why vaccinations work. They can't think of things that such small particles having such a fantastic job on our bodies. Anyway, there we are. That is what Alex Johnson called this triangle. But I'm going to add a fourth corner. Well, actually, it's not me. It was actually done by Alex Johnson himself. He said that what you have to do is to make chemistry relevant to what students come across in their lives. And if you don't do that, you're not getting anywhere. It's going to be very, very difficult. Well, that top part is the fun side. Yeah. The barrier is there. The barrier to understanding. And if you've got this barrier, so you get the misconceptions that everybody talks about. Actually, in my day, it was Worley, you're wrong. But now I'm told I'm a misconception. So I'm happy with that. So there we are, misunderstandings about how practicals work. So that is the show. And one of the difficult items is, in fact, the idea of ions. Even my granddaughter came to me when she was in year 5, and she said, "Granddad, we learned all about things you do, Granddad." I said, "What's that?" She learned about atoms and molecules. So I said, "Did you learn about ions?" "No." So I said, "We'll go back and ask your primary school teacher about if she knows about ions." Anyway, I asked her a couple of months later. I said, "Did you ask your teacher about ions?" She said, "Yeah, she'd never heard of them." And that is the problem. You see, the teachers had never heard of, and so the students are getting the idea of atoms and molecules, but not ions. And really, the best evidence for ions is in the most difficult experiment, and that is the electrolysis of molten lead bromide. So here we're going to see how we do the electrolysis of molten lead bromide. You'll see that I'm using the spirit burner. I've got an LED in the circuit. That's my there, and there's the battery to make it work. And oops, sorry, go to there. Make it work. So I have to do a little bit of glass work. I have to bend the glass into around about a 90-degree angle. You'll notice the flame I'm using is just the flame of a spirit burner. I don't need a roaring Bunsen. You'll notice that the solid, in this case, this is zinc chloride, solid zinc chloride anhydrous, and I've got about 0.5 of a gram in there. On the right is the iron nail. On the left, you can just see, you'll see it better soon, is nichrome wire, which is the anode. So there, we start heating it, and you've got to keep an eye on the LED, and all of a sudden it lights up, and that's when the whole thing's molten. So there is direct evidence of electrical conductivity at this level. Is chlorine coming off? Well, you can use starch iodide paper and it starts to go blue. This is the more traditional material. This is lead bromide. And again, the astounding thing about this is as it starts to melt and you see the reactions occurring, is that you actually see the bromine coming off at the positive electrode. And I can do these on the open bench, not in a fume cupboard, because so little bromine is actually coming off. So that was the idea of the existence of ions, actually from the solid. But now I've got to introduce to you the conductivity indicator, as you see there. This is just a simple circuit. The electrodes, as you'll see in a minute, these are carbon fiber. In the circuit, there is a 500 ohm resistance that there, it shows you there, 500 ohm resistance, and that is there to protect the light emitting diode, so it doesn't blow. Okay, so let's have a look at this one. And what we're going to do here is test this distilled water. Now you'll notice there that the distilled water doesn't conduct a current, so the light doesn't come up. I'm going to take a little bit of just put a little bit of sodium chloride into the puddle and just leave that in there. And you just leave that for about 20 seconds, something like that, and you keep your eye on the LED. And as you do so, it starts to glow. The ions are dissolving, they're solvated, they are diffusing through the puddle to make the LED get brighter and brighter. It was a little wow moment when I certainly got that one to work. So are there any questions about that that's come through, Mark?
No questions in the chat so
okay,
far.
I'm perfect at the moment. That's very good. Okay, so now 4 ways to do a microscale precipitation reaction. But doing something like this is easy. Just that is easy, because that is what we do to do cation tests. That's something like iron 2 sulfate, and I've made iron 2 hydroxide, a nice green precipitate. So that's what you can do. So let's just take it a little bit further and see if we can tease out some of the issues. There is the precipitate for testing of ions. So let's just go back to that and carry on. Now you can take 2 solutions like that, and they're transparent. Okay, so now we just take the pointers in, mix them together, and you get a precipitate. Okay, that's what you would do, like taking 2 test tubes, mix them together, and then the magic occurs. You get this yellow solid just suddenly appearing. Well, let's take it back a little bit further. Where are these solutions coming from? In the UK, of course, the technician is making all these solutions up for the teacher. Where it's like magic. They're just, the students can't see where they're coming from. So what we're going to do now is to make the solutions. So here we have 2 solids. Distilled water in the 2 circles. Just take a little bit of solid and put them into give them a stir so that they mix them together, and then you get the yellow precipitate. Now we're going to do something a little bit more surprising. I hope you see like that one where you take the solids and see that they actually dissolve, and then when they're mixing, you get the precipitate. Now watch this one. So we take the solids from either side, put them into the puddle. You just have to wait a little bit, and there comes the precipitate down the center of the puddle. Fortunately, a colleague of my friend Bruce Matson in America saw this, thought it was really good for his undergraduates, in fact, in America. They're a bit behind. We actually got a paper produced in the Journal of Chemical Education used with that experiment. Okay, so yes, we can use these techniques for the precipitation of ions. The nice thing is that when you're doing testing for ions, you can do all the experiments that don't work. And you're not wasting time getting loads of test tubes and things like this. You just do them on the plastic surface in puddles, and you can see the results. So there we are. The reason I put the line across and dark and white is just so you can sometimes see the pale white precipitates. Solubility and precipitation are the same thing. It's all part of the same thing, but you never realize this if you were to look at textbooks. And you can work out solubility rules. For instance, if you mix together sodium carbonate and copper chloride, you get a copper carbonate precipitate. And the other ions are sodium chloride. Now, I'm going to take a chance here that students know that salt dissolves in water and it tastes salty. So we know it's salty, we know it dissolves. Seawater contains sodium chloride. Everybody knows that. So you've got the idea of the combination of the two of the ions. You can also find that nothing happens with certain mixtures like sodium nitrate and potassium nitrate, or potassium chloride, I should have put there, sorry. Sodium chloride and potassium nitrate, that's wrong. Then, of course, if you do it with sodium chloride and silver nitrate, you will get the silver chloride precipitate. Sodium sulfate, barium nitrate, you find barium sulfate, because you know now that sodium nitrate is soluble in water. So you can build up your solubility rules by doing precipitation reactions. And now, hopefully, you've never seen this before. I'm going to precipitate sodium chloride. Yeah, sodium chloride is soluble in water, but there are two salts. One is lithium, which is 84 grams in 100 mil. Solubility of sodium nitrate is 91 grams in 100 mil. But sodium chloride is only 35 grams at 100 mil. So let's see what happens when we mix together saturated lithium chloride with saturated sodium nitrate. And as you mix them together, start to get the precipitate of sodium chloride. Now, you could not do that in test tubes because you would use so much lithium chloride and sodium lithium chloride, which is quite an expensive chemical. So I've got to see that again because I love it. So we just mix them two together. and we see the formation of the sodium chloride precipitate. It's the least soluble of all those combinations. And I have seen, if you look closer at it, crystals which are cubic. So, any questions about that? Anything?
No, people are being very quiet on the chat, but if anyone does have any questions, please either raise your hand or type something.
Okay, right, we'll carry on then. So here's the diffusing precipitate, silver iodide again. This time I'm using even less material. You'll see the amount I'm using with this. You see the little bit crystals on there? Either side, you put them in there, and it's the easiest one to do. That's why it works beautifully. And they seem to dissolve at the same rate. You nearly always get the line of potassium, of silver iodide right down the center. And you can make do other precipitates as well. Copper carbonate, iron 2 carbonate, the beautiful lead iodide, which starts to sparkle, and the most beautiful Prussian blue, which you get this lovely Prussian blue color appearing. And you can now start to make a model of how these things are working. So we've got the two salts, and they go in there. They're going into the puddle, and when they go into the puddle, they will dissolve. And they will start. Yeah. I'm not good at this. Let's do it. So let's get as far as we got. They go in, and then they start to dissolve. And they start diffusing. And then you get the formation of the slash, and you start to see where these spectator ions, a most difficult concept for 15 and 16-year-olds, or even older, where they're coming from. So you can do a Johnson triangle, dissolving the sudden disappearance of a solid. Right? These are all the things happening. The electrostatic attraction causes reduction in potential in the ions. Actually, there is a very important entropy changes happening as well. It's quite advanced, this dissolving. And then we've got the data interpretation, the idea that water molecules are polarized. They're deflected by electric fields. The dissolved salts consist of a positive and negative ion surrounded by and kept separate by the polarized water molecules. Now, okay, the students might not need to know this, but the teachers do. The students will ask questions, and we have to know the answers. You know, you've got to be prepared to answer these very difficult questions. Okay, so then we have the relevance of dissolving. The fun side, the barrier. And then we get precipitation. We have the symbolic side is there. We have the submicro. We have the relevance. Yeah, every time you wash your hands, you get scum in the soap. That is a precipitate. You can hear a noise, there's sudden rain coming down, a big storm. And so we see the the relevance of precipitation for the students. The fun side, the barrier. So there we are. Reactions have two functions: the kinetics, all about the water molecules in chaotic motion. The solvated ions at some point will meet, and you get the reaction. Thermodynamics as well. So it's quite advanced. You start at year 7 doing the fun stuff and gradually get towards behind. So there's some of the advantages found since being the techniques. We've found the first thing that came to me was that we're improving classroom management. The students are seated to do all these experiments. We've had continual reports that the students' attention is better, and even with the less able students as well. They are focused in to the experiment. They're not listening to all the noise that's going on around them. Time gives you more time to teach. It is helping students, we believe, to develop an understanding of some of these difficult issues about ions, precipitation, and you can extend this to displacement reactions and redox reactions as well. I think it's encouraging new experiments. You will find on the CLEEPS website new videos on hydrogenation of alkenes and liquefying gases and things like this. So I think that is quite. I managed to liquefy ammonia and hydrogenation of propene to make propane, and you can see the two flames. It really is beautiful to see. And connecting this now with STEM initiatives as well, we're using modern materials. We're trying to bring chemistry up into the 21st century with the use of plastics, but avoiding single use, using carbon fiber electrodes, neodymium magnets. Those precipitation reactions, I can do complexes as well. And some of the complexes are paramagnetic, and you can see the effect of the neodymium magnets on these complexes. We're using modern digital balancers. I have tried Arduino, but I sometimes find if when you start to go into this microelectronics field, you find that the chemistry is lost. The attention goes into data logging and the Arduino, and you lose what you're trying to do in the chemistry. But I do think that there is room now for doing some 3D printing of equipment. And for instance, we've made the microscale electrolysis with laser cutting and everything. And so, yes, you hear it here first. We are producing a book. I've been convinced by Sarah Longshore of the ASE that we ought to put this into a book, and we're titling it Understanding Chemistry Through Microscale Practicals. And nobody knows about this except you at the moment. So there you are, hot off the press. We hope it'll come out in January at the ASE meeting. That's a bit of a tall order, but we hope it will soon be after, if not then. So that is it. And hopefully there might be some questions. If not, thank you very much for listening. I hope I've enthused you to take this idea further, possibly in your lessons, or even to try a little bit of microchemistry at home. I am doing this in my bedroom, and at the far end there is my little laboratory. So there you are, you can do your chemistry at home. Anyway, there you are. Thank you very much indeed.
Thank you, Bob. That was excellent.